talked in the past that logic MOVE uses narratives. Well, in narratives, we denote with event calculus in logic MOVE. Event calculus is usually divided into two types of objects. We say that there are fluents and events. And events are things that happen in the world that the event calculus makes happen. Fluents are the things that change in the world as events are happening. There's also relations in the world that don't change, and these we usually call predicates. And then we have actions, which are things that an agent can force to happen. In the actual implementations of event calculus, these are implemented as either fluents or events. There are some syntaxes that are used for these types of things, and the one that's very popular was by Drew McDermott, which was PDDL. And now the original creator of event calculus, Bob Kulowski, uses a syntax called LPS. And then Eric Mueller, who has been doing discrete event calculus, of course, has his own. And then Murray Shannon has his own. I have combined all these into a single unified language. And so I'm going to show you some examples of using these together. First, we're going to take a look at PDDL. Let's go under Logic MOVE. All right, so this is PDDL. It's a pretty expressive language. We can talk about, we have actions, which of course are events in LPS. And then we have conditions, and which are our fluents. They can be used to make plans. You describe things by their preconditions and effects. This is sometimes more convenient, like, for example, if we're dropping an object, that means that it's no longer in our inventory, and it has now the location of being here. So this is another format that's somewhat convenient. Most of these examples are runnable. So in Logic MOVE, we can declare what specific dialect that we're going to be using, and they each have pros and cons. So right now we convert things out of PDDL into the generalized language. So next we're going to talk about LPS. This is LPS. So as I was saying, everything is events and fluents, except we can also have actions, which are a subtype of event. Also in LPS, we can have observations. So here's an example where we are specifying a specific subset of these languages. So for example, this is the farmer, wolf, goat, cabbage, where the farmer has to get the cabbage safely across, and the goat, well, without anyone eating anyone. So here's actions that the farmer can transport something, and fluents that things can be located someplace. And initially this is everybody's on the South Shore, and we have to get them to the North Shore. And these are the rules about that make that happen. So we have fluents, which are things that can change, and we have actions, or which things that agents can do. An example of running this domain. And here we have the steps that happen, that the farmer transported the goat, and the farmer came back in his boat empty-handed, transported the wolf, and then transports the goat back. Now he has the wolf on the other side, so now he can bring the cabbage back, and now he can come and bring the goat. And so all three are united on the other shore. Timeline, which puts them all in a particular form that we're able to look at, and there we go. So these are the various places of the objects over the time. These are the actions. So these are how the fluents have changed. The goat has been moved, and this is the order in which the farmer does these things. LPS can easily solve this sort of problem. Problems that are normally not done in event calculus, if you know the map coloring routine, you know it looks usually nothing like this, but here it's represented in LPS form. So we've got 4 countries, and this shows their adjacency list. We can ask what to do to get all 4 colors on there. And if we had a graphical depiction of this, we would see that everything worked out where there are no countries that are adjacent with the same color. So as you can see, we're able to deal with both dynamic and static problems. Next, we're going to look at Bob's recent work now. He's been doing in the last few months, well, we have a lot more fluents here. They get a little bit more complicated. And these fluents can be as complicated as they need to be because the actual routine that derives them is written in a rule-based language. So, for example, if we had a situation that they wanted to see who has the right of way, it right here compares the angles of the direction of the cars, and that creates the changing fluent of right-of-way fluent between the two vehicles and what place they're at. And during the simulation, we have some observations that we expect to make. And so it is able to make those. Since here we are running it and able to see the animation. Right here is the entire piece of the thing that's creating the animation. And this is only a 31-step cycle animation. Okay, and so we can also view this as a timeline of what happened at each point. Whenever the car makes it to its destination, it's removed from the program. So, oh, actually, this was a broken car that was removed at time slice 15. And the various steps. Okay, so simulation is pretty nifty, but there's some problems. Now we're going to give it a situation that LPS wasn't able to do. Here I'm describing a plant that is about to blow up, and we have to relieve pressure valve by turning off the boiler, opening the valve, and everything. So initially, the plant is not safe. That is our scenario. Just do it like this. We'll say initially the plant is not safe, but now at this particular time point it is. Okay, and now let's run this. Oh, we have to give it a query. All right. Huh. So initially the plant is not safe, but then it is. But we don't know what happened between here and here, do we? I kind of wanted a little bit better output. So I wrote a system that I said unifies the capabilities of these 4 languages. And so one of them is an inductive event calculus prover. Here's the code for that. It's a specialized interpreter. Facts and such scenarios come into here. Actually, initially Murray Shannon had written this thing in 1997 and didn't have all the same abilities that Eric Mueller's had, so I extended it with those capabilities. Also gave it the capabilities of handling LPS problems, which gave it a new, oh yeah, you can see some of the axioms that you'll see like in some of the papers, like by Eric Mueller and so forth. So anyhow, I created a test scenario here that when we compare what we saw happening here, where we just had the plant safe, I want to see how the plant became safe. So let's run my prover. And here it goes. It's figuring things out. And it figured out, okay, what happened was the tank was cool. Actually, I should have had this thing display it in the proper order. Anyway, okay, so the plant is safe at 9. Yeah, I'm using a different numbering system. 8 is actually 9. It's 0 based. Okay, so what it does is it actually says what happened. There was at these different time points, and this here is the proof of why it happened. It's kind of complex how it got there, but figured out, okay, actually what happened was the tank had to get cooled off because the valve was opened, and that was able to drain the tank. And so actually, if you look at the before and afters, it comes out to where, yes, the plant was safe after these particular events, these happenings. So event calculus can be abductive, and that's what we did here with this. This was the abductive version of event calculus, which is part of LogicMu. This can become way more complex too as events are unfold. And this is a real-time system that allows us at any moment to change the scenarios, observe different things, and so forth. Okay, so anyway, what we're doing here is, and in the unified prover, which is this code here, we're able to obduce events. We're also able to do a little bit of induction. I'll show you that as well. So where we guess what the rules of event calculus are as the thing is running. System. So we're doing abductive and discrete event calculus kind of all in one play. And that is going on in order to make derive the solution to this. So so you've seen what event calculus is good for. It's good for making deductions.